Hi everyone. This is the first video for Physics 101 at Mass Bay Community College. This is your friendly and humble Professor Krishna speaking. These videos will act as mini lectures, explaining and illustrating concepts that you'll use for homework and labs and projects. These videos are automatically captioned by Google, so if you need, click on the CC button in the lower right-hand corner of this video to see the subtitles. Sometimes in these videos, I put up calculations on screen, but due to constraints on video length, I can't go over all of the math involved. If you want to look at the calculations in detail, you can pause or rewind the video as needed. Finally, if you have any questions about any of the content in a video, you can contact me in one of two ways. You can either email me with your question, or you can set up a Zoom meeting with me. So let's get started with some basics that we need for this class. In this class, we will express all quantities in metric units, meters, kilograms, and seconds. Most questions in the textbook will be given in meters and kilograms, but sometimes the book throws you a curveball, like giving you a mass in grams instead of kilograms. So let's first look at all the units you'll see. Let's work with distances. In the metric system, the standard unit of distance is called the meter. A meter is about the length of a human stride, a little over 3 feet. 1,000 meters can be symbolized like this, 10 to the power of 3 meters. In the metric system, it's also called a kilometer and symbolized as km. A kilometer is a little over 0.6 of a mile, or pretty close to 5/8 of a mile. You can visualize it as 11 football fields end to end, or the length of a 15-minute walk. When people come to your door asking for contributions to their charity 5K, this is what they're talking about. What about distances smaller than a meter? A centimeter is 100th of a meter, or 0.01 meters, or 10 to the power of -2 meters. It's about half an inch, the width of one of your fingernails. A millimeter is 1,000th of a meter, 0.001 meters, or 10 to the power of -3 meters. It's roughly the thickness of one of your fingernails. Smaller still is the micrometer. It's a millionth of a meter, or 10 to the power of -6 meters. This is the scale of a bacteria. The symbol for the micrometer uses the Greek letter mu. That's that letter that you see in front of the M. And lastly, nanometers. A billionth of a meter, 10 to the power of -9 meters. This is about the length of 10 iron atoms placed side by side. The same prefixes apply to other measurements as well. You've probably run into grams, milligrams, and milliseconds in everyday life. The conversions for these units and others, including non-metric units, are listed in Appendix C of your textbook. Suppose you have to convert units because the book is being annoying. It gives you a measurement of 2 grams, and you have to convert it to kilograms before you can use it. Here is how we handle the conversion. Write the initial value. Then draw a set of square brackets with a fraction bar. Write the conversion within the parentheses. The rule is whatever units you started with, in this case grams, have to go in the bottom of the fraction, and your target units must be on top. Then multiply all the numbers on top and divide by all the numbers at bottom, just like any other sort of fraction. This yields a value in kilograms. 2 grams is the same thing as 0.002 kilograms, or 2 times 10 to the power of -3 kilograms. You might have seen this technique before. It is frequently used in chemistry. If this conversion made sense to you, use this technique to find out how many seconds there are in a year. You will notice that I frequently use exponents to write many of the above numbers. That's because for very large or very small numbers, it's much easier to write exponents than to write out all the zeros. Not to mention, you don't run the risk of miscounting zeros when you're copying a number. This way of writing numbers is part of a standard called scientific notation. In scientific notation, there is always one digit before the decimal point, and the number is multiplied by the appropriate power of 10. So in scientific notation, we would say the number 123 equals 1.23 times 100, or 10 to the power of 2. We would write it as 1.23 times 10 to the power of 2. Likewise, the number 0.0042 equals 4.2 times 0.001, which is 10 to the power of negative 3. So we would write this as 4.2 times 10 to the power of negative 3. And the number 0.000000965 would be written as 9.65 times 10 to the power of negative 7. We won't use scientific notation all the time in the class, but it's handy to know in case you see it in the book. Scientific notation also provides an unambiguous way of dealing with significant figures. In science, no measurement is exact. It's always limited by the gradations of the measuring instrument. For instance, if I measured this pencil with a ruler that's marked only in centimeters, I can say definitely that the length of the pencil is between 6 centimeters and 7 centimeters. Maybe it's about 6.7 centimeters, but I can't say anything more precise. If I reported this measurement, I would say the length of this pencil is 6.7 centimeters. I know that the 6 is correct, but I'm not sure about the 7. It could be 6.6 or 6.8. The digit 7 is uncertain. Whenever you report a number, you are allowed one uncertain digit. In this case, we would say the number has 2 significant figures. On the other hand, what if I measured the pencil with this ruler? It's more finely graded, down to millimeters in fact. Let's measure. It is between 6.7 and 6.8, maybe 6.78 centimeters. If I report this number, then my uncertain digit is the 8, and I have 3 significant figures. A more precise measurement is characterized by more significant figures. If you read a measurement in a scientific paper, you'll need to know how many significant figures it contains. There are a few rules here. First, if you read a number, every non-zero digit is significant. If you see a 0, then you have a decision to make. If the 0 occurs before any non-zero digits, it is not significant. If a 0 occurs between two non-zero digits, it is significant. If the 0 is after all the non-zero digits, it is significant if there is a decimal point in the number, but otherwise it isn't. Why do we even care about significant figures? Because the result that you report from a calculation can never be more precise than the least precise measurement that you took. Suppose we had 2 pencils. You measured one using the first ruler, which was graded in centimeters, and the other one using the second ruler, which was graded in millimeters. What is their total length? The first you measured had a length of 6.7 centimeters. The second had a length of 6.78 centimeters. When you add numbers with differing significant figures, you need to find the highest place value that contains an uncertain figure. The uncertain digit in the first measurement is the 7, and it's in the tenths place. The uncertain digit in the second is the 8, and it's in the 100ths place. The tenths place is a higher place value, so we need to round our result to the nearest tenth when we report it. This is the rule for adding numbers with differing significant figures. The highest place value to contain the uncertainty is the place that you round to when reporting the number. There's a different rule for multiplication, and it's actually simpler. Supposing you multiply 6.7 by 6.78, your calculator will give you 45.426. How do we report this? In multiplication, the result always has the same number of significant figures as whichever input had the fewest significant figures. Since 6.7 has only 2 significant figures, while 6.78 has 3, we have to round our answer so it has only 2 significant figures. In this video, we discussed the units in the metric system and how to convert them. We also looked at how to use scientific notation and significant figures. Now in this class, we will pay attention to significant figures in labs. In homeworks, I'll be more lenient. I'll post the next video in about 2 or 3 days. In that video, we will look at more of the essential math required to excel in physics.